Perfect problem 2, math 251. Use the difference quotient. Maybe I should write out that the difference quotient that says that f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. So a way to evaluate the slope, it's one of the two ways we know to evaluate the slope of the tangent line to a function f of x at a point a. Okay, so if we apply that formula where f of x is x squared, what we get is that f prime of a is equal to the limit as h approaches 0 of a plus h squared minus a squared, that's f of a, divided by h. And this is equal to, if you expand this all out, you get a squared plus 2ah plus h squared. So this expands to these first three terms, and then we got to subtract a squared, and it's divided by h. But what you will see happen, and what will happen consistently down here, is this a squared and this a squared cancel out. And then once that happens, every term in the numerator has an h in it, so we can factor out an h from every term in the numerator and cancel it with this h right here. So this h cancels out, and one of these two h's cancel out. So what we're left with is that f prime of a is equal to the limit as h, let me rewrite that, is equal to the limit as h approaches 0 of 2a plus h. Right, that's all we have left here. And when h goes to 0, that limit is just equal to 2a. So our answer is equal to 2a. All right. This is going to get a little redundant because we do basically the same idea down here. It's the limit as h approaches 0. The only thing that changes now is instead of a plus h squared, it's a plus h cubed. And instead of subtracting a squared, we subtract a cubed. So you got to expand out this, which is kind of a mess. You can FOIL it out twice, or if you happen to know some shortcuts like I do, what you'll end up getting is this. I'm not holding out on you with the shortcut, so these first four terms are this expanded out. I'll actually show you the shortcut down in number 2 of this question. But you expand it all out, however method you want, you end up with this, and what happens is similar to in the first problem, we got an a cubed, and we got a negative a cubed here. Should have been a little bit more careful, that was a cubed that I just canceled out. Okay, and now that those are gone, everything in the numerator has an h in it, so you factor out an h, and this h down here cancels with one of those h's, one of these h's, and that guy. So what we're left with is that this limit is equal to the limit as h approaches 0 of 3a squared plus 3ah plus h squared. But as h goes to 0, this will cancel out and this will cancel out, so we'll just be left with the 3a squared. All right, moving on to part C. Same idea again. There's a reason I'm not just doing these to annoy you. I kind of want you to see this pattern here because it'll be really helpful to develop a pattern. Exact same question, except now instead of a plus h cubed, it's a plus h to the 4th power. And you want to subtract a to the 4th power. So you expand this whole thing out, you FOIL, and then you FOIL again. And if you did everything right, you got a to the 4th plus 4a cubed h plus 6a squared h squared plus 4ah cubed plus h to the 4th. Again, I'll show you how you can come up with that a little bit easier soon. And then from that, you got to subtract a to the 4th, and you divide that whole huge mess by h. And just like above, the first term here cancels out with this last one, and every other term has an h in it, so we can cancel out this h with this h, one of these, one of these, and one of these. And the key point is that what is left is 4a cubed and then a bunch of stuff that all has h's in it. 6a squared h plus 4ah squared plus h cubed. I guess this is the, what if I can save this? This is the limit as h approaches 0 of this mess. And the key is, the reason I stated it like that, all these things have an h in it, is because when h approaches 0, all of these go away. So really all you're left with is the 4a cubed. So kind of the pattern I was hoping that you'd see if you do enough of these is that in each case the answer, 2a, 3a squared, and 4a cubed, you can kind of see where that comes from. Really, it's the second term in this big expansion without the h in it. And that will be important because we can develop a rule that will tell us what is the derivative, what we're figuring out here, of x raised up to any power. Here we're only doing it with 2, 3, and 4. So anyways, what I'm getting at here, what if we asked x to the 10th? All right, you could do this in theory. I mean, you could figure out that f prime of a is the limit as h approaches 0 of a plus h to the 10th power minus a to the 10th divided by h. But what I said is don't actually do it here because I don't want you to expand a plus h to the 10th power. It would take you forever if you actually multiplied those all together. A trick you can use is this thing I keep alluding to. It's that the coefficients of a binomial expansion are given by Pascal's triangle. What Pascal's triangle is this thing that I'm making right now. The way you get any digit, like the way where this 4 comes from, is it adds the two numbers above it. So 1 plus 3 is 4. This 6 is 3 plus 3. 3 plus 1 is 4, and then 1. 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. You can keep doing this. Maybe I should have picked a smaller number than 10 because we'll need a lot of these. Maybe I'll just, well, I'll do it. Why not? I can do it. 1, 8, 28, 56, 70, 56, 56 being this plus this, 28, 8, and 1. 2 more rows I'll have to do. Or no, I guess this is the last row I have to do. Nice. Nope, 2 more rows. 8 plus 28 is 36. 28 and 56 is 70, 84. 56 and 70 is 126. I got some patterns going on here. And finally, the last row is a 1, a 10, a 45, 120, 210, 252, 210, 120, 45, 10, and 1. So anyways, the reason I created this whole thing is because a plus h to the 10th, if you expand this whole thing out, the coefficients are given by this last row right here. What I'm saying is that a plus h to the 10th is 1 times a to the 10th plus 10, the second number, times a to the 9th times h, plus 45, a to the 8th h squared, plus 120, a to the 7 h cubed, and so on. But I'm not going to write that all out. I'm just going to write stuff. So we keep going with this whole expansion to get this, and then subtract a to the 10th and divide by h. But the key thing, all that's important here, is that we have an a to the 10th here, like we did above, and an a to the 10th here. Those cancel out. And then we can cancel out this h in the bottom with this h and an h from all this stuff, right? I don't know how to write that. We take an h out of all this stuff. But all this stuff was divisible by h squared. So maybe I even write this. Note, all of this stuff is divisible by h squared. So when I cancel out an h with all this stuff, every single term still has an h in it. So what that does is it lets me evaluate this limit. It's the limit as h approaches 0 of 10a to the 9th plus stuff, but all this stuff is divisible by h. Every term has an h in it. So the limit as h approaches 0 makes all this stuff go away. They all have an h in it. 0 times anything is 0. Everything here goes away. So our final answer is just equal to 10a to the 9th. So the derivative of x to the 10th is 10a to the 9th. And that will end up being, maybe you can already see the pattern, but using this fact, we're going to come up with the rule, and it'll let us take any derivatives. But for now, this is all we want. That will be the end of this perfect problem.